Hello everyone, let's go ahead and take a look at theorems for real polynomials. The first one that we have is called the fundamental theorem of algebra. And basically what it says is that if we have a polynomial of degree n, where n is greater than or equal to 1, this polynomial has at least one zero that can be written in this complex form a plus bi, where a and b, of course, are real numbers. If p of x is a polynomial with degree n, then p of x has exactly n zeros, some of which may be irrational or complex. Okay, so let's just go ahead and take a look at an example of this. Let's say, for example, we have this particular function here called p of z, set equal to 0, and it's a fourth degree. What that means is that if we go ahead and take a look at the degree of p of z being 4, then that means that there has to be 4 roots. Now we're going to continue with this problem and say z is going to be equal to 3 plus I, and we want to go ahead and find out what a and b are. But for the purposes of the fundamental theorem of algebra, that's the information that it gives us. This polynomial is of degree 4, therefore there has to be 4 roots, and the roots have to be in this particular form. At least one of them has to be in that particular form, and some of them may be irrational or complex. Okay, so let's continue. It says the sum and products of the roots theorem. Now, it says that for p of x being equal to the polynomial set equal to 0, where of course a sub n is not equal to 0, then the sum of the roots is going to be equal to the opposite of a sub n minus 1 divided by a sub n, and the product of the roots is going to be equal to negative 1 raised to the n power times by a sub 0 divided by a sub n. Now, if you want to go ahead and take a look at the proof of that, the proof is located in the textbook. What we want to do, though, is we want to be able to apply this to go ahead and find the sum of products of roots so that we can then go ahead and solve some problems. So let's go back to our example here. So let's say, for example, we know also from this problem that this particular degree 4 polynomial has a root 3 plus I, and we want to find out what a and b are. As we know that there's 4 roots, and we know that the roots, if complex, are always going to be in conjugate pairs, then we know that 2 of the roots is going to be written as 3 plus or minus I. If this is going to be one of the roots, then of course the conjugate is going to be a root, and so we know that both of those are going to be roots. Therefore, we know that z squared plus a sub 1z plus a sub 0 equals 0 is going to have these 2 roots. So it's going to be some kind of quadratic that's going to produce those 2 roots. Now what we're going to do is we're going to use the sum of products of roots theorem to actually go ahead and determine what a sub 1 and a sub 0 are. And we did this before with quadratics, but let's go ahead and use this here to see how it applies. Now if we go ahead and take a look at the sum of the roots, of course, here are 2 roots, is 3 plus I plus 3 minus I. The product of the roots, of course, is going to be 3 plus I and 3 times by 3 minus I. Now, if I go ahead and take a look at what the sum of the roots are, the sum of the roots is going to be the opposite of a sub n minus 1. Now, when we go ahead and take a look at this here, the value of n is 2 because this is a second degree equation. So that means that the opposite of a sub 2 minus 1, which is just simply the opposite of a over 1, a sub 1, divided by a sub 2, well, a sub 2 right over here is going to be a value of 1. Then we know that that is actually going to be equal to the sum, which is 6, therefore a sub 1 is equal to negative 6. In the same respect, if we go ahead and take a look at the product of the roots, we've got negative 1 to the second power because, of course, n is going to be equal to 2. A sub 0 divided by 1, I know that 3 plus I times by 3 minus I is going to give me 10, so therefore I know that a sub 0 is going to be equal to 10. And now I've found the quadratic factor of p of z based upon these 2 complex conjugate roots. So I know that z squared minus 6z plus 10 is indeed a factor of that. Now, if we want to go ahead and find out what a and b are, we need to go ahead and consider what are the other 2 roots, or what is the other factor that is going to actually generate this degree 4 polynomial. Well, we already know that this degree 2 polynomial is going to produce 2 roots. We need 2 more roots, so let's go ahead and generate another quadratic. And notice that the quadratic's coefficient of z to the 4th is 1. So therefore, if I multiply these two together, I'm going to come out with z to the 4th, which is consistent with the coefficient of z to the 4th in the original polynomial equation. So what I'm going to do then is I'm going to say, well, I don't know what this linear coefficient is, and I don't know what that constant coefficient, that constant term is going to be. So I can then go ahead and just say that this general value here, this general quadratic, multiplied by what we know is already going to generate these 2 roots here, multiplied together to give me 0, will actually be something similar to that. Now I'm going to go ahead and use synthetic multiplication to come out with this long expression here. Now notice what I have is this has got to be equal to this. That's what we're trying to do. We're trying to show that this and this are equal. So now what I need to do then is I need to go ahead and take a look at the coefficients and equate the coefficients. So I know that the coefficient of z to the 3rd, which is minus 6 plus c, has to be equal to negative 3. So therefore c is equal to 3. And I also know that 10d must be equal to 20. So therefore I know that d is equal to 2. Now that I know what c and d are, of course I can now go ahead and find out what a and b are. So a is going to be, of course, 10 minus 6c plus d. And if I substitute those values in, I come up with a is equal to negative 6. If I do the same thing for the coefficient of z, which is going to be the value of b, and the value of 10c minus d, equate those 2 substitute values, and I come out with b is equal to 18. So what I've done then is I've been able to now go ahead and find out what a and b are. So I know that the original polynomial, degree 4 polynomial, should be written as z to the 4th minus 3z cubed minus 6z squared plus 18z plus 20. And that should be equal to 0. So notice what we've done is we've used the fundamental theorem of algebra to determine how many roots we have. And I've also used the sum and product roots theorem to go ahead and determine what one of those factors, the quadratic factor, looks like. Okay, now we haven't done anything with the rational root test yet. And we'll go ahead and take a look at that right now. It says if p of x is a polynomial, and p is going to be all the factors of a sub n, and q is going to be all the factors of a sub 0, then the possible, now this is going to be a very important word here, the possible rational roots of p of x will be in the form x is equal to q over p. Okay, so let's take a look and continue this example here. Now, here again is our exact same polynomial. Now what we want to do is we want to just go ahead and find all the 4 roots of this. Now how do we do that? Well, we already know that z is equal to 3 plus or minus I is going to be the 2 roots of this particular polynomial. And when we did this expansion with the multiplying by the other quadratic factor, we found that c was 3 and d is equal to 2, and therefore we know that this is going to be the factored form of this particular degree 4 polynomial. We already know what the 2 roots are from here because that was given to us in the question. We just need to go ahead and find out what the 2 roots given by this quadratic factor will be. So if I set that equal to 0 and use the 0 product property by factoring, I can come up with z is equal to negative 2 or z is equal to negative 1. Now notice that the 4 roots now that we have, which is consistent with the fundamental theorem of algebra, are going to be 2 complex conjugates and 2 rational roots. Now let's go back to this whole thing about the rational roots test. If we were to go ahead and take a look at p, which is going to be the factors of the coefficient of this particular first term of our degree 4 polynomial, which is 1, then that means that all the particular integral factors of 1 is going to be plus or minus 1. Q is going to be all the integral factors of 20. So here are all the integral factors of 20. Now if I go ahead and take a look at what those roots are, if they will be rational, the possible roots are all going to be in the form of q divided by p, and q is going to be q over there, that entire list here, divided by plus or minus 1, and so therefore we're just going to come up with all the values of q. Now what would that mean? In order for you to go ahead and test to see whether or not these will indeed produce a particular root for the original polynomial function, we just need to go ahead and substitute all of these values into P of z. If it's equal to 0, then we know we found one of our roots. Now for this particular case, of course, notice that z is equal to -2 and z is equal to -1 is in this particular list. Now the thing is that we said that it's a possible, the rational roots test will give you the list of the possible rational roots. If there are rational roots, it will be in this list. If your original polynomial does not have any rational roots, then of course this list will not provide you with any zeros. So it's going to depend upon what the original polynomial function. Okay, so let's kind of go back to what we're dealing with here and just kind of summarize. So remember that the fundamental theorem of algebra is going to tell you basically the degree of your polynomial is going to give you how many roots you actually have. Some of them will be complex and some of them may or may not be real. Okay, after that you can use the sum and products of roots theorem to help you determine, say for example, a quadratic factor of your polynomial. And then after that you can go ahead and continue to go ahead and use some of those ideas that we've learned from the previous sections to go ahead and continue to find out what all of the roots of your particular polynomial will be. Then the last thing, of course, is that if you need to go ahead and test for any of the possible rational roots, you can go ahead and use this here to just quickly determine whether or not there are rational roots for your original polynomial. So we'll take a look at some of those questions in class the next time that we meet. See you later. Bye-bye.